see there is this dip here. This dip is caused when basically we are transitioning current. We can see that this current is transitioning from this phase to this phase. Right? So we have a transition, and that transition causes this dip. So anytime we have a transition from one phase to other phase, we have this dip. And this dip is related to the inductance of the motor and the reverse recovery of the diodes. If we can eliminate, and as this inductance of the motor increases, this dip will become deeper. And some motors you cannot use BLDC algorithm. When the inductance becomes too large, the BLDC algorithm will not work for those motors. At least in this type of scheme, where you have a high side PWM, just because you need at that point of time better control over the current. You need all PWMs, which allows you better control over the current to control the motor.
But larger the inductance, the motor is more stable and more. It takes a long time to change the current, right?
I think that's one part of it. Long time to change the current, but you really want to change the current within the rotational speed. Let's say if you want to go at 100 RPM, or let's say 1000 RPM, right? And if you 1000 RPM, if I cannot change the currents in a phase within the 1 by 1000 time period, then I don't have a motor. Because when you turn on the switch, the motor current is going to ramp up, but it may get to the final value when we actually should have phase 3 current. For example, let's see here. Let's say you want this current to go. You turn the command on, and this current is up in a matter of microseconds, right? Right. Now, what happens when you have a large inductance? This current may go like this, and when it goes like this, what happens? That means I cannot establish these currents and these currents. So the motor has a terrible lag, the current has a terrible lag, and as a result, you have a very poor power output. Your motor may not rotate at all. So the switching strategy has to match your type of motor. And this way, at least on Spice, you can verify how well your motor is going to behave before you pick a strategy.
No, just I'm talking about only the tip portion. For a given motors, two kind of motors with L equal to some L1 and L2, where L1 is greater than L2. The tip portion will be smaller for a motor with higher inductance. Maybe I can increase or decrease the switching frequency according to the motor inductance. So then I can see a smaller tip for the higher inductance motor.
If you change the frequency.
Yeah.
Yes. Yes. Yeah. If you go from 20 kilohertz to 1 kilohertz. Yes.
I can see a small tip also.
I think so. I think you'll be able to see.
Here the problem is you're shifting from one phase to the other phase. So that is because of the reason of you're shifting from one phase to the other phase. So that phase difference shifting will always be there whether your inductance is high or low.
Correct.
So in that case, how will the dip goes?
See, you have. Let's think about this for a second. We really have let's see here.
Can you use a black pen or something?
Sorry.
Can't see.
Right, so we have a current flowing through here. and we want to change from this switch to this, basically from this phase to, let's say, this phase. So when I turn off this switch, right, what's going to happen? When I turn off this switch, this diode is going to come on, right? Right, this diode is going to, so this current is going to continue to flow like this. So the transition here, basically, this, if I draw this inductor current, goes to 0, while this current builds up. Now this time period here is essentially, so when this is going down, let's say the voltage here, the inductor voltage here is essentially, you can say, L di by dt. And this is equal to, if you take neutral voltage to be half of the supply voltage, you could say, let's say this is V dc by 2. So that's the equation. Now, if you have this equation, delta I by delta t, I guess you're pretty much dependent upon the voltage and the inductance. So it is going to do, and of course the value of the current. What is the value of the current? Have I got this right? So you have got L di by dt is equal to V dc by 2. So depending upon, essentially, I can even take it further. It's Li max divided by delta t is equal to V dc by 2. So delta t is the time period we're talking about, is given by Li max times 2 divided by VDC. So I guess it is independent of the switching frequency, which is the point you were making, which I guess is the correct point. Because depending upon this current value, depending upon the inductance value, you basically are deciding, and the supply voltage, you're deciding what your delta T is. So that is independent of the switching frequency. Okay, so here you have a motor with about 242 microhenry of inductance, and then you have got essentially.
But the delta I will be depends upon L, right? If I take delta I by delta T equal to VDC by 2L, so the delta I is inversely proportional to 1 by L. So the ripple of the current will be inversely proportional to L.
Yes.
So that does make me that my ripple will be dictated by the inductance value.
Your ripple, yes. Your ripple, yes. But not the dip. Not the dip. You're talking about this ripple, right?
Not only that, during the changeover also. During the changeover also, the dip will be again depends upon the inductance value.
I don't know.
During the transition phase,
Right.
again the dip will be controlled by the inductance value. Okay.
Yes.
During the transition phase also, the dip, the magnitude of the current
Transition.
fall.
Delta T. Delta
Yes.
T. Yes. Is correct. Delta T is controlled by the inductance value. That is correct. That is correct. You're talking about the rise time. The rise time and the fall time, right? Yeah, because the rise time and the fall time, when they cross, you have a up and a down. So that obviously is related to the inductance value. Okay. So here are three waveforms which we got from the simulation, and the current seems pretty decent for this particular motor. 20 kilohertz, 242 microhenry seems like a decent target for high side PWM. This is some more waveforms to look at. We have the I feedback. Now we have got these dipsy-do here within the I feedback. This is obviously when we have a transition, basically 6 times a cycle. We have error amplifier output. and then we have a PWM output. So these signals, so if you go back to the circuit, so we are looking at high feedback, we're looking at error amplifier output, and then looking at PWM. Those are three signals we're looking at. Okay, so and then we basically up the reference to see if the circuit still behaves linearly. So we can see not only does the current change, the color of the waveforms also change. They become colorful. So we actually, when we pasted them, we forgot to do some one step. So that's why you see this black and white. Anyhow, so we got color. We were able to get the correct color waveforms here. So here you can see the current waveform still pretty well behaved for our simulation because it sees.
It will be at the time of transition.
Yes. Right. Right. Exactly. Exactly. Here you may be able to see it. So you have got this occurring at 7 milliseconds, and then this is occurring at about 8.25 milliseconds, about 1.25 milliseconds, which is, I think, about 100 hertz, right? About 900 hertz, and our frequency is 133 hertz. It's about 6 times that.
Well, there are small glitches on the PWM signal, even that I could not see.
Those are the convergence issues.
The second
Yes.
issue, on the second
You don't have
transition,
it.
I don't see that.
You don't have it.
Yeah,
I think here we had a convergence problem. The system recovered, but we didn't have a convergence issue here.
But we have a duty cycle block, right? That doesn't help. We are limiting the duty cycle to 1% to 99%. That doesn't help.
No. See, that's one of the issues, Spice has, that these convergence problems are kind of unpredictable. And see, so a lot of people, a lot of other systems have come out, which have claimed to have much better convergence than Spice-based programs. But Spice-based programs, also people, because it has been extensively used, people have found ways to go around convergence issues. And I have 3 slides which I'll mention at the end, dealing with the convergence issues of Spice. And actually, that when Simplorer came out, Ashish is here from ANSYS. So when Simplorer came out, first time, that was the biggest claim to fame, was they had no convergence issues. And because they use different kind of algorithm. Spice uses Newton-Raphson method, and so Simplorer, I don't know what algorithm Simplorer uses, but it's a different kind of algorithm which claim to have better convergence issues than Spice. Anyhow, so we still run into convergence issues in Spice, and that's where you end up building models quite but it's become with the components we have built, it's a whole lot more robust than it used to be.
Question. You have changed the frequency here of the PWM, right? It's 20 kilohertz. 20 kilohertz. You have changed the reference signal.
Right.
Will that change the amplitude of the back EMF, or
It's still the same. Still the same. This is the power output. Here, let's see. Let me just blow this up a little bit so we can talk about it. Okay. So here also you can see that that ripple is getting transmitted to output power as well. So during transition, you have got issues with that part. Now you want to minimize this if you have if there is a torque ripple which is occurring, which is, let's say this is occurring at 1 kilohertz, may not be an issue for your performance, but still, that's always a sore part in BLDC drivers. This is causing a ripple, and here the level here, this is about 80 watts. And the way we have calculated this power, there is a power function in PSpice, and it's called W. So I'm going to just slide this up so you can see the power function. So the power function here essentially is, we calculate the power at a node, so it's W and 1, 2, 3, 4, 5, 6. So 6 sources which we talked about to build back EMF. So we compute the power from that point.
Would this also be available in the student version of PSpice?
Yes, it's available in the student version of PSpice as well.
How do you determine the power divided by P? Your parameter block inventory is P parameter.
Right, no, yeah. We are not really calculating the torque here. This is constant speed. Right, we're not calculating any. Okay. So let's see. Getting back to now, we'll come back to this high and low side PWM. This is just a slide which shows the performance with high and low side PWM. You can see just that the performance, the waveforms look a whole lot better than high side PWM. So we'll come back to this when we run the demo. You still see some convergence issues, but PSpice recovers at these convergence issues. But you have the little bit better behaved feedback signal and error amplifier. Not a whole lot, but a little bit better behaved than what we had. This is P out with the high side and low side PWM. Again, your ripple reduces slightly. The magnitude of this reduces. Now, we use a signal called average. Not the smartest way of doing this, but that's one thing you can calculate. The best way is to do FFT, the fast Fourier transform, to dissect the components of the power when you're trying to read the power. But here also there is a signal, we used average signal, essentially. It's not the smartest way of doing this, but that's one option. You can quickly see power input and power output. All right, let's see if we can fire up a demonstration.
Typically, how long it will take to run the simulation time?
It's not, for this particular demonstration, it should be less than a minute. So what we have here, we have used capture schematic. Not my favorite program. I still like to use text-based circuit files because I think the nodes which are generated by capture are unreadable. If you look at the circuit file, it has got nodes which are 6 digits long. So, but anyhow, it's convenient to visualize your circuit using the capture schematic. So here, we have within this capture schematic, we have essentially 6 schematics: 3-phase BLDC, 3-phase motor, gate drive logic, PI amplifier, and then we also have an amplifier from ST Microelectronics, which is there just to show a difference between ideal components and non-ideal components. So let me open the first schematic. So what we have done here, and I'm going to blow this up. So we have this particular switch, switch 1, is an ideal switch. And the way we have created this ideal switch is we have got certain text files which are included. And this ideal switch is a text file. And essentially, now this one is a bidirectional switch. Okay. Now, if you want to simulate, so this is a text file. Basically, you have a sub-circuit called switch. It has got drain, source, gate, and gate ground. So it's got 4 terminals. And the model we use is idle switch, where we have set R on to be 0.005. That's the difference we have. So we control R on to be 5 milliamps. And you can change that parameter as you like. You can also IR has, or most of the manufacturers have PSpice models. So you can definitely plug the model in from International Rectifier or some Fairchild or from any other manufacturer. But we like to use this one because it's simpler to use and more robust from a convergence standpoint, and your circuit file doesn't blow up. The minute you get a model from manufacturer, all of a sudden your circuit file is 4 or 5 pages long. So, and also the runtime will increase because you have got quite inbuilt nodes in the model.
Does this have a voltage drop across the device?
The voltage drop is basically the resistance.
There's no separate voltage drop.
Right.
And no drop is considered for the diode.
Yes, let's look at the diode. So the diode.
This is including the diode, right?
No, this is not including the diode.
Switch.
Yeah, this is a simple switch, and this is a simple switch. And if you want to simulate a directional switch, you can use the same diode